We're in Chapter 9, Hypothesis Testing, and we're going to be covering sections 9.1 and 9.2. I'm going to mix them together because I just think it works best to get some of the theory in about hypothesis testing and do a bunch of hypothesis tests. Now, remember, for the last few weeks, we've been working on confidence intervals, this technique or skill we learned to come up with a range of reasonable estimates for a population mean based on a point estimate or sample mean from a population. We're going to do something somewhat analogous, but we're going to phrase it differently. Here, we're going to have a preconceived notion of what the population mean already is, and we're going to collect data and decide whether the data contradicts that presupposed population mean or not. And the technique is called hypothesis testing. And we're going to define some terminology, but of course, we're going to go through an example to illustrate all of this. So remember our battery life example from before, right? Where we sampled 81 Lenovo ThinkPads, and we had a mean battery life of 7.3 hours. And suppose we knew that sigma equaled 0.6 hours, okay? So just keep that in the back of your mind as I'm going through this example. I'll erase it because I'll say this a bit later on. Okay. So anyway, suppose additionally that Lenovo claimed that its ThinkPads on average had a battery life of 7.5 hours. Okay? I.e. that they have a mean battery life. Now, maybe this doesn't mean literally every Lenovo has exactly a 7.5 hour battery life, but if you were to average them all together, on average, their battery life would be 7.5 hours. Okay? So then we would expect a random sample of ThinkPads to have a mean battery life of, roughly or approximately 7.5 hours. Right? Now, why might it not be exactly 7.5 hours in a random sample? Random variation. This is something we've discussed before a little bit. Random variation leads to random samples having statistics that differ from parameters. Right? And that's why, right? No tricks. Just when you sample, you're going to get statistics that might differ. Ideally, they don't differ all that much, but still, they might. Okay, now remember, we had n equals 81 ThinkPads. We had a sample mean or point estimate of 7.3 hours. And we assumed that the standard deviation for battery life for the population was 0.6, okay? So we're going to test this data against Lenovo's 7.5 hour battery life claim. So what do you think, just looking at this data? Do you think that it's that the data... I'm going to cross out the word suggest here. I'm going to write contradicts what Lenovo says. Do you think the data contradicts their claim of 7.5 hours of battery life or not? Do you think it doesn't contradict? I know it's a double negative, but this is how it's phrased. And I'll just, I'll give both. All right, well, let's consider both situations. It does contradict. Well, 7.3 is less than 7.5 hours, and n equals 81 is a large sample. right? So is there really going to be all that much random variation with a large sample? On the other hand, maybe the data does not contradict the claim. And maybe that's because, maybe because random variation could mean we have x bar equals 7.3 despite mu equaling 7.5, right? So either situation's possible. Let's see what the data actually suggests. So what we're going to do is we're going to perform something called a hypothesis test, which is a statistical method that determines the statistical significance of the sample mean, assuming a certain population mean. First off, when you perform a hypothesis test, you want to state your, hypotheses. And there are always two hypotheses that we state. There is the null hypothesis, which we denote HO, and that's the current accepted value, right? It says basically that mu equals whatever value, right? In this case, it would be 7.5. Okay, but in general, it'll be mu equals some number. Okay. Meanwhile, the alternate, sometimes it's referred to as the alternative, and that's referred to as H1. You might also see HA, but the book calls it H1, so we'll call it H1. And that's going to be that mu is not equal to whatever accepted value, or that mu is less than the accepted value, or that mu is greater than the accepted value. You could see all three of these alternate hypotheses, only one at a time, but any of these three is an option. Okay? So anyway, in our case, given our context with Lenovo, ThinkPads, and battery life, let's think about what we would say. Well, the null hypothesis is always going to be the same, right? It's always going to be battery life equals a certain amount, right? So here it's going to be mu equals 7.5 hours, i.e. the mean, well, not the man, the mean, I guess I said ThinkPad. The mean ThinkPad battery life is 7.5 hours. Okay? What's the alternate hypothesis? The alternate hypothesis, now, if we think about it, we could say that the mean just is not 7.5 hours, but do we really think that Lenovo would undersell its battery life? Do we really think it's possible that their battery life is really like 8 hours or something like that? I would say no. Companies tend to overestimate their products. They tend to overhype their products. So I think a reasonable alternate hypothesis from this situation is that the Lenovo ThinkPad battery life is less than 7.5 hours on average. The mean battery life is less than, let me actually write this in red right here. (7.5 hours). That's the only difference between the two hypotheses, right? Let me actually maybe just write this in red so it pops. Okay. Next up, we're going to find the standard error, which we still denote as SE. Now, in this case, we know our standard error is going to be SE equals sigma over root n, which in this case is 0.6 over 9, right? Because remember, n equaled 81. Okay. And then we are going to find, now, this is a little bit technical. I'm just going to put this in parentheses because this is what's technically going on, but we don't actually need to calculate this by hand. What's really happening is we're finding the z-score of our sample mean within the sampling distribution, which in this case is going to be z is going to equal, you don't need to write this down if you don't want to, but it's going to be x bar minus mu all over our standard error, right? Which in our case is going to equal 7.3 minus 7.5 divided by 0.6 over 9. And I think we could actually work this out by hand. Again, don't worry too much about this because this won't show up in Excel. But this is going to equal 0.2 divided by 0.6 over 9. And if you just do the multiplication out, you wind up getting, oh, sorry, this was negative 0.2. You wind up getting negative 3. Just erase that real quick. Negative 3. Okay. Anyway, using the standard error, we use, again, we're going to be using Excel, or you could use Table A2 in the book to find the p-value of x, which is the probability that we would get a value, I guess I'll say in this case, well, in general, it's going to be more extreme than x bar, but in general, in our case, it's going to be less than. I'll write this in red. In a random sample of size, in this case, n equals 81. Okay. Now, we can use the chart, but let's go ahead and use Excel. So if we go ahead and get out Excel, for this, I am in one sample Z because we are assuming that we know the population standard deviation. We're just going to put in our stuff, right? Put in our data. Now, at this point, we need to decide on a confidence level. The same way that intervals are usually at 95%, we're going to choose 95. Oh, actually, I guess never mind. Since it seems to be different, we'll choose a significance level. 0.05 is the usual significance level. It's 1 minus the confidence level. And our hypothesized mean was 7.5. See, our test statistic was negative 3. That was the negative 3 we calculated earlier. But you see, let's maybe up these decimal places maybe to 4. That's a little bit better right there. Okay. So if we go right over here, see how this corresponds to our alternate hypothesis? And we get a p-value of 0.0013. Let's snap a picture of that. And I'm going to just circle this in red right here. Maybe I'll even just circle this part right here. Okay. Since P equals 0.0013, what this means is that there's a 0.0013 chance we'd get X bar is less than or equal to 7.3 hours in a random 81 laptop sample, assuming mu equals 7.5 hours. So, assuming that the mean battery life was 7.5 hours, it is very unlikely, right? It's like a 0.1% likely that we would get such a low mean battery life from an 81 laptop sample. Right? So, typically the standard is that P be less than 0.05. We got a P value that's a lot less than 0.05. Okay? So that would suggest that we don't believe H naught to be true. We don't believe the null hypothesis is true. But a p-value of 0.05 would suggest that the null hypothesis may be true. Since p equals 0.0013, which is less than 0.05, we state the following. We reject the null hypothesis and conclude, I'll save the conclusion for the space below. We then conclude mu is less than 7.5 hours, i.e. the mean, again, not the man, the mean ThinkPad battery life is less than 7.5 hours. Again, these are made up numbers. I am not pro or anti-Lenovo, just making stuff up. So anyway, what did we do? What did we do to perform a hypothesis test? Well, for starters, we stated the null and alternate hypotheses. We found the standard error, which in our case equaled sigma over root n. We then found again, I'll put this sort of in parentheses here, and then the z-score, which was z equals x bar minus mu all over the standard error. But in our case, Excel kind of took care of that. Then we find the p-value. I'll put these in parentheses here. Corresponding to your z-score. Determine your level of significance, which we denote alpha, and then compare p and alpha. If p is less than or equal to, I guess we say less than or equal to alpha, then reject the null hypothesis. If p is greater than alpha, then fail to reject the null hypothesis. Okay, and then state your conclusion. Let's take a look at another example. We have data, blah, 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 blah. December 8, 2018 suggests that this was the deal. Okay, random sample of 50 homes had a sample mean of that. Okay, So again, suppose we unrealistically make an assumption about sigma equals, in this case, 150. Can we conclude that the mean price in 2019 differs from the 2018 price? Now, note that word differs. First off, we're going to state our hypotheses. In this case, we're going to say mu is going to equal 522.8 thousand. Okay? The alternate hypothesis, because of the word differs, is going to be mu does not equal this guy that I'm just going to copy. Okay. Okay. If you see the word differs, then it doesn't mean less than, it doesn't mean greater than, it means not equal to. Okay? So at this point, we're going to say, okay, we have this. Find the standard error, find your z-score, etc. Really, in our case, we just kind of enter this stuff into Excel. Here, our sample mean was 553.3. We're assuming the population standard deviation was 150, and we randomly sampled 50 houses. Note that it says use an alpha equals 0.005 significance level, and that's what we did right there. And we are hypothesizing that the mean is 522.8. So for not equals, you see how we get that as our answer? Maybe I'll just screenshot that little part right there. All right, and so what we get is that our p-value equals 0.1505, and note that that is greater than alpha, which equals 0.05, right? Again, we're getting 0.05 from this guy right here. All right, and again, we got our p-value from this guy right here. Okay. So what's our conclusion then? Fail to reject the null hypothesis. So even though we got a sample mean that was a bit higher than we might have expected, there's not enough evidence that the mean, was it house price? Yeah. In 2019 differs from the mean house price in 2018. That's all we've got.